What the hell is that thing doing on my precision granite surface plate? With its non-standard threads and its terrible surface finish. I'm a simple machinist. Is it too much to ask for a proper carbon steel construction? But that name looks familiar somehow. Keithley. That's kinda cute. It just displays a lot of digits. 6.5 of them. You know, funny story. Back in the days before my metalworking career started, I had this inexplicable desire for digits. Okay, it can stay, but I think I've got a much better place for it than the granite surface plate. Hey guys, thank you so much for 100,000 subscribers. It's an absolute honor that so many are interested in my silly little presentations. To celebrate this milestone, I thought I'd bring back a classic that I haven't shown in a while. The ever-popular Keithley repair. That idea is as always sabotaged by eBay sellers falsely advertising their old Keithleys as defect. This adorable Model 155 microvolt null detector needed only a new set of batteries. And a thorough cleaning because the old ones from '95 left us a little something. Ugh. Before we take it apart any further, here's why this ancient meter is interesting in the first place. There are a couple of reasons. A thermocouple consists of at least 2 different metals and junctions between them. If there's a temperature difference between the junctions, a small current wants to flow. It's called thermal EMF and it will haunt us for the rest of this video. Luckily, Keithley 155 is so sensitive that it can detect and quantify these usually very small effects. It's so sensitive that it can detect the heat of a normal red laser pointer. I've shown something similar before with a certain heat flux meter. Also an interesting device, but I don't like how it tries to lure you into physics by giving you something as absurd as kilocalories per square meter hours. Instead, why don't you attach a good old wire to a piece of steel and have your microvolt meter sense deformation, because that would stretch the wire and increase its resistance. No need to rely on my sketchy handiwork though. Because this is exactly how a strain gauge, aka load cell, works. This chunk can measure forces equivalent to 300 kg with the same deformation sensing technique. Check out the deformation caused by this bolt. There is a little bit more going on in that load cell though than just a sticky taped piece of wire. We've got 4 very equal pieces of wire forming 2 equal voltage dividers. So naturally the 2 central voltages are also equal, no matter what kind of excitation voltage you apply to the top and bottom nodes. However, when one of the 4 resistances, the one that's actually attached to the metal body, shifts ever so slightly, so does the voltage between the 2 central nodes. The fact that these slight shifts happen around 0 and not around the much higher excitation voltage is useful, because our Keithley null detector, one can tell by the name, is an expert in all things that happen at or around 0. The circuit with the 4 equal resistors is called a Wheatstone bridge, and it's all over the place. This temperature-stabilized enclosure, for example, has one, with a resistance thermometer instead of a strain gauge. Back in the 60s, this unremarkably looking box was one of the best voltage references one could buy. It accomplished such a world-class performance simply by keeping the internal temperature at 30 degrees C precisely. And curious tinkerers like me out. Behind double or triple shielding and a few interlocks to prevent overheating, it was filled with these glorified glass batteries, aka Western cells, which in turn were filled with mercury and some electrolyte. When kept undisturbed in a perfect environment, these are still absolutely supreme voltage references. To keep them undisturbed means that you can't just take a voltmeter and measure them though. You would allow a small current to flow through the voltmeter's internal resistance, and that would change your glorified battery's output voltage forever. That might be a bit of a deal breaker for the volt nuts who like to voltmeter the hell out of everything. but no problem, Keithley's got you covered. The proper way of utilizing such a high-end voltage reference is to dial in a secondary reference with a differential measurement. Because you're generating equal voltages on both sides of your voltmeter, its internal resistance doesn't matter. No current will flow either way. And because of the outstanding microvolt sensitivity, you're really able to hit that sweet spot precisely. Oh, 7.1 something something volt. That sounds familiar, doesn't it? Those were a few features of the Keithley Model 155. It's still cool. Let's see if we can figure out how they accomplished that in 1975. I didn't exactly have to carbon date the 5% resistors in here. It's the date code on multiple components. Construction-wise, there is not a lot going on. Some beautiful mica and film caps which will last forever. But the original electrolytics and tantalums are good candidates for a timely replacement. Even though they have survived for 44 years with a perfectly fine ESR. I've never seen a multi-turn potentiometer like this before. It's sort of a planetary reduction gearbox situation, but with ball bearings. Here's the circuit in an extra simple simplification. The input signal goes through some attenuation, because the meter is supposed to be able to measure up to 1000 volt. Next, there's a little oscillator that's constantly connecting and disconnecting the attenuated input signal from a capacitor. Caps only let AC voltages pass, so the newly created AC waveform, whose amplitude is proportional to the input voltage, gets amplified and again passed through a cap. That strips away the amplifier's unwanted DC offset that otherwise would have easily overpowered our microvolt signal. Now we've got an amplified, input voltage dependent, offset voltage free AC waveform. That just needs to be demodulated based on the easily available oscillator state. And that's the 1975 interpretation of a chopper amplifier. Whether or not we get to see a more modern version depends entirely on how quickly we reach the 100k subscribers. It will be close, because this thing has been listed as defect correctly for once. Beautiful. A stuck power switch, a constant overflow display, missing segments, and a missing millivolt input cable. So this is a Model 181 nanovolt meter, built in 1980. That means it's only 5 years younger than the previous microvolt meter. But it's about 3 orders of magnitude more sensitive. Had Keithley released more and more sensitive voltmeters every 5 years, they would already have to be further than Yoctovolt. The most sensitive voltmeters today can measure only picovolts, however. And I think even in this relatively modest device we'll get to see some of the physical non-negotiables that hinder further progress. So this beauty is made up from 4 PCBs. The mainboard is boring, power supplies, optical isolation, and a microcontroller and associated components. It's noteworthy that there's no precision analog stuff, no PTFE standoffs, and no guard traces on here. That way a little bit of universal snake oil spray won't do harm. It may not save the power switch forever, but at least it rejuvenates it and lets me proceed until I find a proper replacement. The front panel board is connected astonishingly poorly, with this press-fit ribbon cable terminal. I have no scientific evidence to support my claim, but I'm going to say it anyway. That sucks. See, that's clearly not my fault. I'm going to replace that with a precision IC socket. But alas, it was not what caused the missing segment. The real culprit becomes obvious when looking at the schematics. Since all of the C segments and the 200 mV LED are missing, I'm going to make a wild guess and say that Q208 is responsible. Dead or alive, such a general purpose PNP is worth next to nothing. So I'm just going to snip it to make desoldering safer and easier. Wanna know what else has made desoldering much easier for me? Skillshare. Wait, no, not today. Surely I can't be the only one struggling with these obnoxious little rests of solder that just sit there in the center of holes, refusing to be wicked up from either side? It doesn't feel like it's worth firing up a special desoldering tool for. But since I got an air compressor, I keep finding more and more purposes for it. It's also great for the cleaning afterwards. Before having access to an infinite amount of compressed air, I used to feebly try and soak up as much IPA and dissolved flux as possible in pieces of tissue paper. So primitive. Now I can just blast it all the way without leaving any fibers hanging on component legs. And I can even get to the stuff that's hiding underneath parts. And that's a working front panel, as easy as that. Now we've got to figure out why it insists on displaying O-flow all the time. I was really hoping for this to become a triumphant, edutaining repair project, but the problem literally started sending out SOS smoke signals while I was setting up. Well, we've got an overheating voltage regulator, and that's usually caused by an overheating consumer somewhere. In this case, a shorted tantalum cap. With a little tantalum protuberance maybe. Ductility test says no, that's just a drop of solder. I'll order replacements for all 4 of these suicidal blobs. But for now, an SMD bodge will have to do. That just fixed board number 3, the nanovolt preamp, and the overflow issue along with it. While we are there, let's check it out. I hope you remember our friend thermal EMF from earlier. To exist, it needs a metal difference and a temperature difference. So the design focus in this assembly is going to be avoiding at least one of the two. Because they can't really match cable and connector temperatures to that of the internal junctions, they have to use equal metals for those. And because you can't really solder that well or make semiconductors from copper, they are trying to equalize the temperature of the entire sensitive area. The extraordinary cleanliness for low leakage currents that was so important in other Keithleys we've seen is not really that critical here. I mean, it's probably beneficial around those film caps though. Because them holding their charges perfectly is crucial for this implementation of a chopper amplifier. Here too they are alternating between applying the input voltage and 0 to the preamp. But this time, instead of further processing the signal as if it was AC, they are storing the 0 offset voltage on the large film capacitor in such a way that it reverse offsets future readings. That way, Keithley 181 is able to continuously auto-zero and to subtract its own internal offset voltages from the displayed result. In the readily available service manual, there are numerous pages where they are talking about Johnson noise in film resistors, copper-legged JFETs, and this little container of thermal compound. I'd love to say that that's too much to cover in such a short video. But the truth of the matter is that I don't understand all of it, and I'd just be spreading fake news if I kept on talking about this stuff. So I would suggest that we start playing around with this newly repaired nanovolt meter, until I did my homework and am able to show you a DIY picovolt neuroscience squid. Oh, almost forgot. Last but not least, the analog board is cool. The voltage reference is an LM399 ovenized Zener diode, giving this thing an absolutely respectable stability even 40 years later. But why does anybody need a nanovolt meter in the first place? Well, material science, metallurgy in particular. Also, everything related to superconductivity. And the name is giving it away, nanotechnology of course, like carbon nanotubes and stuff. I, right now, can really only demonstrate a few things related to the metrology side of things. Not even that. I don't even have the correct input cable for the thing. But maybe I can make one. This military connector fits, but it uses different metal pins, from the custom ones that Keithley must have ordered back then. The result is an unacceptable offset voltage, even with a direct short. I'll just shove my test subjects in there with low noise toothpicks as artificial pins. Freely hanging PVC isolated bare copper wires can perform nicely, but just by changing their relative position slightly, I got a drastically different reading. A PVC isolated twisted pair prevents that, but it does seem to generate a few nanovolt here and there. The best ordinary cable for nanovolt purposes I found in my arsenal is called RG316. It's a PTFE isolated silver-plated copper coax. It seems readily available and cheap even. I tried to pause all vital functions for a moment so as to not disturb this measurement, but I just had to move and ruin it here, damn it. Let me just solder a terrible spade connector and a normal screw terminal to it, with the absolute worst roll of solder I've ever used. Wait, what? Oh, I think thermal EMF is acting in its favor right now. Gotta let it recover completely from the soldering. Yeah, that's pretty bad because of the multitude of metal transitions in there. Pomona makes a range of low thermal EMF connectors. Those are made from directly gold-plated copper. They aren't cheap, but they do precisely what they claim. Originally, I wanted to replace my Solartron input connector with a few of them, because at the time I didn't have that input cable either. But now I do, courtesy of a generous EEV Block forum member who gave that to me for free. Thanks, Doc. It's a beautiful Swiss-made Fischer connector with 4 shielded Teflon-isolated, silver-plated copper cables. That doesn't sound like a source of a lot of unwanted nanovolts, but since I'm now able to test that, I will. Solartron isn't really such a specialized nanovolt performer, so it can have noise and just general inaccuracy in its least significant digits. But theoretically, this digit corresponds to this one, so choosing the best kind of input connector will yield the best kind of measurements. I thought I'd do this test surrounded by a lot of grounded and temperature-stable steel. Pomona's low thermal EMF stuff is reading something between 20 and 30 nanovolt, with an uncalibrated meter whose noise specification happens to be 30 nanovolt peak-to-peak precisely. I'm measuring Solartron's input cable from one end through both connectors and presumably multiple solder joints, all the way to the front-rear switch. So it's a bit of an unfair comparison, but still a decisive result. So coming up soon, new Solartron and Keithley input connectors, an LTZ1000 based voltage reference for Solartron, it has been powered on continuously ever since I made that video, and just more copper for everything in general, I guess. And that's it for this 20-minute marathon. Thank you for watching.